Hello everyone. In this lecture, we'll be learning about some other members of circuit families that include pass transistors, which we have learned earlier. Then we'll be learning about two other members, lead and CPL, and how those circuit family members are useful, and what are the benefits and the disadvantages, and what is their area of application. We'll be learning about all of them very shortly. Next, we have to discuss about pass transistor circuit. We have already learned about the pass transistor circuits. The pass transistor circuits use each of the circuits use one PMOS and one NMOS network, which are alternatively switched on and off. And these pass transistors are sometimes added linked with static CMOS circuits as well. And this is an example of 2 to 1 mux. For example, when S is 0, the output is equal to B. When S is 1, output is equal to A. So this is a pass transistor circuit. We have learned about it in earlier lectures as well. Another member of logic family is LEAP or lean integration with pass transistor. What it does is, in case of pass transistors with the NMOS, there is a PMOS involved. But in case of LEAP, the PMOS is neglected. PMOS is not used. Then what happens? If S is equal to 1, A flows to this point, and through the inverter, it we get output is equal to A bar. If S is equal to 0, B flows outwards, and through the inverter we get output is equal to B bar. Now, the problem, we have used pass transistors because the NMOS pass 1 poorly, but 0 it passes 0 well. So if A is 0 or if B is 0, there is no problem, it will be passed well. But if A or B is 1, there is a problem that NMOS passes 1 poorly. Since suppose A is 5 volts and it passes here, it comes 4.5 volts. But that won't be a problem. Why? Because this 4.5 volts will, after passing through the inverter stage, it will become 0 volts, which will then switch on this PMOS. If it switches on this PMOS will charge the output capacitance present here, and as a result output will rise to 5 volts. We are just giving it an example for 5 volts logic. So in case of using PMOS for every transmission gate, we are using just one PMOS, which will be used to charge the output capacitance. And using this, we can actually you get along with using a weak PMOS to pull the output fully high, and the ratio constraint is maintained, and the LEAP, this circuit family LEAP is very beneficial because since the number of PMOS decreases, the area of the circuit decreases by a large portion, and here is where LEAP comes into play. Another logic is used, which is complementary pass transistor logic. It is a very similar to LEAP logic, but in case of LEAP logic, we get feedback from the output. In complementary pass transistor logic, we do not get any feedback from the output. What we do is, using NMOS we create the gate, and using NMOS we create a gate using the complementary inputs. Then what happened is, obviously since this is normal input and this is complementary input, suppose if S is equal to 0, what happens is, here we have B bar and here we have B. Now here we have B. Now obviously either B has to be 1 or B bar has to be 1. Let us suppose B is equal to 1. Then B bar becomes 0. Since they are complementary, B bar becomes 0. If B bar is 0, from here it pre-charges this MOSFET, and since it pre-charges this MOSFET, this point is pulled up. This point is pulled up, and again from B we get output is equal to B bar here. And again, and since B bar is 0, NMOS has already passed 0 efficiently. So here in the output we get B. Again, if we are considering if B bar is equal to 1, then B will automatically become 0. If B is 0, it will be passed efficiently, and in output we will get B bar. And if B is 0, this will switch on this MOSFET from this VCC this point will be pulled up and this capacitor over here will be charged, and B bar will become strong 1, and as a result in the output we will get B. So what we can see is, using complementary pass transistor logic, we are actually pulling up the output whenever necessary, but we do not anymore need to take feedback from the actual output of the system. That is, the output is being pulled up from the logic created by the inputs and not the feedback from the output. It avoids the need of ratioed feedback, and this is a dual rail form of pass transistor logic. That is, we have Y and Y bar, both of them are present, and we input true and the inputs are true and complementary, and the outputs we get are also true and complementary. There can be optional cross coupling from rail to rail swing. That is, there can be an optional noise element involved. So pass transistors have researchers have investigated pass transistor applications in 1990s, and it has lots of benefits over CMOS, as they suggest that they are of high speed, they consume less power, they consume less area, but they are not generally used. They are not generally used because in case of CMOS, our inputs only drive the gates of the MOSFETs, but in case of pass transistor, our inputs does drive diffusion region. That is, what do I mean by that? Suppose this is a pass transistor, this is NMOS, this is PMOS. Here if we have this, we will have this bar. So here we have our input. So in general, input is to drive the gate. If input drives the gate, what happens? There is no gate current involved since gate are insulated. But in case of pass transistors, input drives the diffusion layer. As a result, there is a current flow involved, and as a result, sometimes it consumes more power, and also the delay effects are increased. As a result, at this moment, pass transistors are generally not used. In some special circuits such as memories, where small size is required, and pass transistors are still in use. That's all for this lecture. If you have any query regarding circuit families, feel free to post your queries in the discussion box of BUX, and I'll try to answer them as soon as possible. Thank you.